My name is Juan Caicedo. I am a professor and I'm the chair of the Department of Civil and Environmental Engineering here at the University of South Carolina. These are my notes in innovation. So my job as a chair is to enable people to do innovation as professors. So professors have basically two roles. They teach classes, which is what most people know, but the other half of their life, maybe more half of them, is to actually create knowledge. And that's where the innovations come into place. Innovation comes in different forms. Sometimes it comes as an idea of when a person sees a need, and the researcher might have an idea how to solve that need. And my job as a chair is to be able to support the faculty to be able to do their job and create ideas, be able to test those ideas in a lab like this, and then being able to move those ideas into products perhaps, and they can be then used by society. I think it is possible to create an environment for people to learn how to innovate. I think it's extremely difficult to teach it itself, but you can really develop the environment where you can foster that. That's one of the things that is important for us actually as instructors, is realize that it's very difficult for you to teach and to quote unquote force somebody to learn. All you can do is really create an environment and give the instructions to the students about how to do this, right? So a big part for me is to be able to enable the grad students to be able to give them some latitude in what they want to do, talk to them, okay, what do you want to pursue? Why do you think this is important? So that innovation aspects, you start learning how to do innovative, how to test your hypothesis, and how to be able to move your ideas into something that's a little bit more hands-on and be able to publish those results.
You have some very specialized equipment here, right? Some that's just one of only 4 or 5 in the world?
Here in the department, we have a lot of different equipment that we can use, and it's very specialized. We have, for example, in the area of geotechnical engineering, we have a centrifuge, and that centrifuge spins soil around so we can increase gravity, right? So that's a technique that geotechnical engineers use. It also has a shaker, so you can actually simulate an earthquake as you spin the soil around. And there's only 6 centrifuges with shakers in the whole country. So it's a very unique type of equipment that we have here. We also have a pit right in the background where you can have a foundation. At the same time that you have part of the structures, you can do experiments in soil structure interaction. Right now, for example, we have a small track, and that track, you see the soil underneath the track, but we also see the structure, right, the rail and the ties in there, and we can test the whole thing together rather than testing only the structure or only the soil. In this lab in particular, we are 5 people working in this lab. There are all sort of different things happening right now. We have a faculty member that is working in creating stronger walls so they can be standing during a tornado or a hurricane. In particular, he's looking at the way that the wall protects the people inside, but when you have basically projectiles going through the air and hitting the walls. So he is embedding plastic inside the walls. It's a recycled material anyway, so it's something that we're throwing away these days, so we're just making the walls stronger that way. In one case, you can see a wall where if you take a 2x4 and you shoot it with an air cannon that we have, it basically went through the wall, it looks like butter. You can see the shape of the 2x4. In the other case, you can see that the wall has actually been damaged. But when you look at the experiment, the 2x4 actually didn't go through the wall, right? So even though you have damage in the structure, the structure is protecting the people that are inside the structure, right? And that is just by adding little pieces of plastic in the masonry itself. We have a lab where researchers are able to do scale models of levees, and you can run water through the channels and study how the water will break the levee and what would be efficient ways to close that levee breach. We had other labs where we look, for example, at sediment transport. So if you have sediments in the ocean, how are the sediments going to transport through time, right? And that has many applications that can help us have a sustainable infrastructure. We have another faculty member that is looking at creating a new type of concrete that can be used for concrete ties in rail. This, we hope, will extend the life of these concrete ties, making the railroads better, but also cheaper to maintain in the long term. And some of the work that I do, I'm looking in floor vibrations. We're looking in two aspects of that. One of them is we want to measure floor vibrations to know what happened with people. For example, if somebody falls, we want to know that looking at the floor vibrations. But we also want to make structures more comfortable. And today, one of the problems that is happening is structures are vibrating a lot. Because of people walking on them or interacting with the structures. We want to understand that a little bit better. The idea about the floor vibrations started actually not by me, but another faculty member here in chemical engineering. His name is Harry Plon. And he was listening to a medical doctor talk about the challenges that they had with elderly. And one of the things that the medical doctor said is, well, people fall down, they spend a lot of time on the floor, and in some cases, people forget to wear the devices in their neck, or they just don't want to bother people and they just don't call for help. When he was listening to this, he just come to the idea, oh, wait a second, we can probably do something with floor vibrations. And he just came to my office the next day, told me about the idea, put me in contact with the medical doctor, and then we started applying for grants to different institutions. The Alzheimer's Association was the first grant that we got, and from that, the research started. So what we hope will happen in 10 years is this new knowledge becomes patents, right? That companies are now going to start using them to put sensors on the floors. And now you can have people who are indirectly being observed, quote unquote, by the floors without the need of having cameras. So you can have, for example, a person who is 80 years old and maybe has initial parts of Alzheimer's, but that person is protected by the house itself because the house is actually sensing or feeling whether or not the person is okay or not. There's so many other applications as well. You can use this for security systems. You can use this even for biometrics in some cases. You can detect the gait patterns of the person. So there are many other applications that we've thought about, but we're still in the fundamental research aspects to create that knowledge. The biometrics aspects are really an aspect where you can actually try to identify what person is in the building. When you walk, every time that you strike the floor with your foot, we can actually detect those vibrations. And the speed in which you walk, the stride in which you walk, and all those things are personal characteristics of you in particular. So we can actually determine whether or not you come to work or not, for example. At least that's what we hope the work will lead us. Not necessarily to know if person have come to work, but more about is a person who's not supposed to be in this building there or not, right? That's the main idea. A few years ago, so I have 3 kids, they're all boys, and so our house shakes by nature. That's what our kids do, right? So a few years ago, I instrumented my house, and it was amazing when we look at the data that you can tell when they wake up, you can tell when they take naps, they can tell when they go for lunch, right? Just by looking at the amount of vibration in the house. So you can actually use this to be able to determine whether or not the person is still healthy, right? If the person is changing patterns, that might be an indication that the person is getting sick. And then you can have a doctor being more proactive and going and calling the patient rather than waiting for the patient to get so sick that then needs to go to the ER.
So I want to kind of get your backstory. Tell me how you got into structural engineering.
Right, so I'm originally from Colombia, and back there we have a lot of earthquakes. When I was a kid, actually, we had an earthquake that was very strong and devastated the city where I was living. So that had a big influence on me. I wanted to get into earthquake engineering. And my dad is a civil engineer. My grandfather is actually what is called a roads engineer because civil engineering was not available when he graduated. And of course, they had a huge influence on me as well. So I started my studies, looked at the field of earthquake engineering, and then really fell in love with vibrations and all the things that you can do with vibrations. Moved to the States in '99 to do my PhD. I went to Washington University in St. Louis, looked at how we can use vibrations to try to determine whether or not a structure is healthy or not, and then came to the University of South Carolina after that to work and do research and train students. Innovation is an interesting thing. I think sometimes it's just ideas. When we as engineers see a need, we just come out an idea of ways that we might be able to solve that. The next step is to be able to test those ideas, right? In some other cases, is as an incremental progress, right? Somebody says, maybe we can do a concrete that is stronger, and you start thinking about it and do incremental progress on making that concrete stronger by adding some chemicals or by adding nanoparticles or things like that. So I think innovation comes in those two different forms. Sometimes it's just a revelation, it just comes to mind when you see the need. In some other cases, it's just progress that is done over time. As a professor, it's very important to stay innovative by going to conferences. That's one of the main things that we do. And sharing your research with others so you can receive feedback whether or not what you're trying to do is feasible or not. But at the same time, going and talking with other people about what they're doing and see how what you do can cross-link with what they do to create new things. Innovation happens at the edges of the disciplines, right? So, for example, it is very difficult for us to recreate concrete. Concrete is already created, right? We can improve it by taking something from other disciplines, learning what they do in their disciplines, and trying to look at the edges of our discipline and incorporate those ideas. So it is very important for us as researchers to talk to computer scientists, to talk to people in other disciplines, right? And learn what they're doing and see how what they do can help what we do, and for them to learn how what we do can help what they do. Right? So that is very important. That multidisciplinary aspect is extremely important for innovation. Every single faculty does pursue these multidisciplinary aspects. So we understand that we on our own will not be able to write the computer code to do the data analysis, do the experiments, know about the fundamentals of physics of what's happening. So we actually seek other people to help us explain the physics, to write the code, to interpret the data. And with that, we create multidisciplinary groups that then drive this innovation. Team dynamics is very important when you have multidisciplinary groups. Communication is extremely important as well, because one of the challenges that we have is what we call one thing, other discipline might call it slightly different, right? So we want to make sure that these groups are communicating effectively. We want to make sure that these groups have the tools to be able to succeed and have actually the funding. A big part of what we do is seek funding from federal agencies and state agencies to actually test our ideas and then drive this innovation. A big part that we do as professors is to seek funding to test out our ideas. And that is perhaps, I want to say, more than 20% of our time, right? When we have an idea, we want to test it. But for that, we need the equipment, we need the grad students to help build the specimens, and test our hypothesis, and be able to actually do the experiments and look at the data. There are several agencies that we collaborate with this. At the federal level, for example, we have the National Science Foundation, we have the National Institute of Standards and Technology, Federal Railway Administration, and many other agencies that we work with, the DOE, DOT, and all these things. So what we do is we write these ideas and we look at what agency might be interested in moving this idea forward. So it's interesting. I think it's actually a connection between the researcher and the agency as well, because you as a researcher need to be aware of what the agencies would like to fund, right? And it's coming to a point where you have interesting research for the agency, but also the agency would like to fund your research. We spend a significant amount of time writing proposals, and then those proposals go to those agencies, they get evaluated, and based on that evaluation, they decide to fund or not fund the project. It is amazing the amount of writing that we have to do as professors, and I think as graduate students as well. And the main idea is things happen, but it is only useful when you communicate your findings with other people, right? And you can communicate these findings in a verbal way in conferences, but the most efficient way is to actually write it down in papers, in reports, or even in patents that they can be used by companies. And all of this happens in writing. The main thing that drives me is the vision of sustainable and smart infrastructure. It really does. If you think about the future, we're going to have cities that are going to have autonomous cars. We're going to have buildings that are going to sense the way we walk. We're going to have aqueducts that are going to know whether or not the water that you're drinking is safe or not. We're going to have processes in the city that's going to take, for example, food waste and create energy out of that food waste. And all of those things are actually happening here. Here is where we create the knowledge for those things to be possible. And that really is what drives me. I think failures are actually a huge part of innovation. It's a huge part of research. Failure happens in many different ways. Like, for example, when you write a proposal for the National Science Foundation, only about 8% of them get funded. So we get failures in that way many, many times, right? A quick story about failure that I remember very clearly when I came to the United States was I started my PhD and I had a really difficult time understanding my professors because my English was not very good. And by the middle of the semester, I was calling my family and say, well, there was, nice couple of months in here, but I'm gonna probably be back home in a month or two because I'm not gonna be able to make this, right? I thought it was a big failure for me to come to the States. But then after that, I realized, well, I just need to buckle up and just try to push as much as possible and see what happened with these classes. And at the end, I actually performed pretty well in those classes. So one of the things that I learned with those experiences is that failure should not stop you from trying to accomplish what you do. Failure is only a way for us to learn what we need to do to be able to accomplish our objectives. And that happens all the time in research, right? Many of the things that you see published or you see in the news is only what worked. But behind those things that work, there are hundreds and hundreds of attempts of things that fail. But that is really part of the innovation process. There are also many very rewarding times of the work that we do. One that it happens to me almost every week is when I'm working with a student and you can see the bulb going off and say, oh, now I understand it, right? Now I understand where we're actually getting these results of this experiment. That is extremely rewarding for me as a person who is advising a student. There is also some moments where you're trying an experiment. I have one of the projects that we had many years ago was to try to develop sensors that are moving sensors. So when you have a structure, most of the sensors are actually attached on the structure. The idea we had is, well, what if we start moving the sensors through the structure and then you can have a signal that is a function of time and space now. And we did the experiments and we would look at the data. It was just so evident that things that were just working beautifully that you just get this sense of, yes, we were able to dream this. We did the experiments and it just works great. So it is really a good sense of accomplishment. If somebody would like to pursue a career in being innovative and doing research, I think the main things that they want to do is persistence, of course, but also to be able to have a good team. I am only here because of the work that my grad students did in the past. I'm only here because the faculty that I work with, because we're able to work together and having these multidisciplinary teams that we can move things forward. It is very hard to do innovation on your own. I'm not saying that it's not possible, it might be possible, but it's extremely difficult. And anyone that you see that is doing innovation is because they have a huge support team that is able to accomplish those objectives. In civil engineering, for innovation, there are many tools that are needed these days. I think sensing is a big part of civil engineering these days. If we are able to do experiments, we need to be able to sense that, right? So learn how do you make this sensing and put it into a computer for the data analysis is a big part. I also think that it's very important to be able to have knowledge of computing itself. Because these days, computers are becoming a tool that is very needed for anything that we do, right? Whether or not you're doing things numerically in models, but also in the lab. Because any experiment that you do is going to create data. And that data needs to be analyzed somehow, and those computer tools are extremely important. It's also very important for a person who wants to do innovation in civil and environmental engineering to have those fundamentals of physics and chemistry, right? Those fundamentals of engineering as well, mathematics, right? So you can actually be able to solve for some equations, or be able to understand the physics of what's happening when you're doing an experiment, or be able to think about the reactions that might be able to help clean water, right? Or things like that. Something essential for me in my bag every day with my laptop. I mean, I don't know, my lunch maybe. One of the things that we really need to have every day is being able to have open communication with everyone. These days, being able to do teleconference with other people, other researchers in other places, right? Being able to communicate effectively through email is extremely important. Being able to communicate with the grad students when they come to a meeting, right? That's something that is extremely important for all of what we do as professors.
What's that sort of one thing you have to have?
Email. I mean, in reality, but it's not necessarily email per se, but it's the fact that you're being able to communicate effectively with other people, right? I think that goes again to the idea of creating the environment where you want the person to be have some latitude in creating some ideas and testing those ideas. Well, you'll be able to have that open communication channel where the person is telling you, hey, I want to try this, and you give some advice. Oh, that's a really good idea. Why don't you try it in this slightly different form to see what happened, right? So that communication is extremely important. One of the most fun parts that I had through my career as a researcher was when I was a grad student. Because when I was a grad student, my advisor was very wise at trying to protect me from other things, like, for example, finding the research money, right? And other things that we as faculty need to take care of. So grad students really is, when you're a grad student, you really have the freedom to be able to test things. You have a little bit more free time to be able to go to the park, go ride in the park, and something might come up when you're actually at the park riding something. So you saw someone driving a bike down the road, and that sparked an idea, right? So I think about the time when I was a grad student, and that was a really fun time. It allowed me to do experiments that I wanted to do. I wanted to throw ideas to my advisor and say, what do you think about these ideas, right? And you have a little bit more flexibility in your schedule and flexibility on your responsibilities that you can actually be a little bit more innovative that way. As a faculty, I think our innovation is a little bit more pointed because we have more experience of what things might work and might not work. So as a faculty, I have a lot of fun when I actually write proposals, because those are the stages when you have an idea and you're actually forming that idea. It's like taking a sculpture, right? And you have a general idea and you start chiseling little parts of it until you actually make it a little bit more manageable. And then you send this to a funding agency, and if it gets funded, it's a lot of fun to have that and go through the process of testing whether or not those ideas are worthwhile or not. My name is Juan Caicedo, and those were my notes in innovation.